This is SpaceTime, Series 28, Episode 41, for broadcast on the 4th of April 2025. Coming up on SpaceTime, mysterious red sprite lightning seen over the Himalayas, shocking Spherules on Mars, and a new geological map for the asteroid belt. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have captured rare images of red sprite lightning high above thunderstorms in the Himalayas. The mesmerizing display of more than 100 of these red sprites were photographed by Chinese astrophotographers Angel An and Chu Changdong over the world's highest mountain range at an observational site located in the southern Tibetan plateau near one of the region's 3 sacred lakes. The breathtaking celestial event included dancing sprites, rarely seen secondary jets, and the first ever recorded case in Asia of green afterglow at the base of the nighttime ionosphere. A new study reported in the journal Advances in Atmospheric Sciences sheds light on the driving force behind this grand sprite display. By analysing the parent lightning discharges, the authors discovered that the sprites were being triggered by high peak current positive cloud-to-cloud lightning strikes within a massive mesoscale convective system. This suggests that the thunderstorms in the Himalayan region have the potential to produce some of the most complex and intense upper atmosphere electrical discharges on Earth. Lacking precise timestamps for detailed analysis, the authors developed an innovative method to synchronise video timing using satellite trajectories and star-field analyses. This allowed them to determine the exact occurrence times of the sprites and link that to their parent lightning discharges. The study revealed that the parent lightning discharges occurred within stratiform precipitation regions of mesoscale convective complexes stretching from the Ganges Plain to the southern foothills of the Tibetan Plateau. The events recorded the highest number of sprites during a single thunderstorm in South Asia, suggesting that thunderstorms in this region possess upper atmospheric discharge capabilities comparable with those on the United States Great Plains and offshore European storms. Moreover, the findings indicate the storms may generate even more complex discharge structures, potentially influencing atmospheric coupling processes with significant physical and chemical effects. Sprites belong to a colourful group of transient luminous phenomena with fairy tale names such as sprites, blue jets and elves. Their transient vertical column-like plasma flashes high in Earth's atmosphere, often resembling a glowing reddish jellyfish with tentacles streaming down. They're thought to be large-scale electrical discharges at altitudes of between 50 and 100 kilometres above the ground, triggered by rare positive lightning that originates in the anvil head of a thunderstorm cloud where positive charges tend to accumulate. Now, positive lightning is about 5 times as hot and powerful as the regular type of lightning we normally see, which is technically known as negative lightning. Positive lightning also lasts about 10 times longer, allowing it to strike many kilometres from the storm. In fact, that's the feature which has led to the famous expression, a bolt out of the blue. Unlike negative lightning, which occurs either inside the storm cloud or from the base of the thunderstorm cloud to the ground, positive lightning travels outside the cloud, striking the ground directly. Sprites are sometimes preceded by a red halo emission, lighting up a millisecond before the sprite, about 70 kilometres above the initiating lightning strike. Then there are sprite halos. They look like 50-kilometre wide discs and are thought to be produced by a weaker version of the same ionisation processes which produce the sprites. Next we have blue jets. Blue jets are very bright narrow cones of plasma seen above thunderstorms, propagating upwards into the stratosphere from the cloud tops, often reaching heights of 80 kilometres or more. They're thought to be associated with strong hail activity during thunderstorms, and their colours believed to be caused by blue and near-infrared emissions from neutral and ionised molecular nitrogen. Another closely related phenomenon are blue starters, which are thought to be shorter, brighter versions of blue jets, only reaching to about 20 kilometres in height. And then there's a third type known as gigantic jets, which are thought to be bigger versions of blue jets. And finally we have the elves. They're flattened expanding reddish concentric rings that often appear as dim expanding 400 kilometre wide glows lasting for just a millisecond. They've been seen at altitudes of 100 kilometres above thunderstorms and are thought to be generated by the excitation of nitrogen molecules due to collisions between electrons energised by lightning from the underlying thunderstorm. Sprites, elves and jets are all very little understood, seldom seen, but a fascinating part of our upper atmosphere. This is SpaceTime. Still to come, shocking spherules discovered on Mars, and scientists develop a new geologic map of the main asteroid belt. All that and more still to come on SpaceTime. NASA's Mars Perseverance rover has discovered a strange rock composed of hundreds of millimetre-sized spheres. The find has shocked scientists who are now working overtime to try and understand their origin. It's now been 2 weeks since the Perseverance rover arrived at Broom Point, situated on the lower slopes of the Witch Hazel Hill area on the rim of Jezero Crater. Here, a series of light and dark-toned bands of rock were visible from orbit. Now last week, the 6-wheel car-sized rover successfully abraded and sampled one of these light-toned beds. And it was from this sampling workspace that Perseverance spied a very strange texture in a nearby rock. The rock, which has now been named St. Paul's Bay, appeared to be comprised of hundreds of millimetre-sized dark grey spheres. Some of these occurred as more elongated elliptical shapes, while others possessed angular edges, perhaps representing broken spheral fragments. And some spheres even possessed tiny pinholes. It's all raising questions about the type of geology that could produce these strange shapes. Of course, this isn't the first time strange spheres have been spotted on Mars. You may recall back in 2004, NASA's Mars exploration rover Opportunity spotted so-called Martian blueberries in the Meridiani Planum. And since then, Curiosity observed spherules in the rocks of Yellowknife Bay in Gale Crater. In fact, just a few months ago, Perseverance itself also spied popcorn-like textures in sedimentary rocks which had been exposed in the Jezero Crater inlet channel near Avia Valles. Now, in each of these cases, the spherules have been interpreted as being concretions, features that were formed through the interaction with groundwater circulating through pore spaces in rock. However, not all spherules form this way. Here on Earth, they can also be formed by the rapid cooling of molten rock droplets from volcanic eruptions, or through the condensation of rock which is vaporized during a meteor impact. Each of these formation mechanisms would have vastly different implications for the evolution of these rocks. So, scientists need to work hard to try and determine their context and origin. However, the St. Paul's Bay was a float rock. That's a term used by geologists to describe something that's not in place. Scientists are now working to try and link the spherular-rich texture observed at St. Paul's Bay with the wider stratigraphy at Witch Hazel Hill. Initial observations have provided tantalizing indications that could be linked to one of the dark-toned layers identified from orbit. Placing these features in geological context is crucial for understanding their origin and determining their significance for the geological history not just of Jezero Crater's rim, but also for the red planet beyond. This is SpaceTime. Still to come, a new geological map of the main asteroid belt between Mars and Jupiter, and the splendours of the Southern Cross and its 2 pointer stars, Alpha and Beta Centauri, the blue supergiant Canopus, and the Lyrids meteor shower are all among the highlights of the April night skies on Skywatch. Scientists have put together a new geological map of the main asteroid belt between Mars and Jupiter. Knowing from what asteroid belt debris field and meteorites hitting the Earth originate from is important for planetary defence efforts. The new findings, reported in the journal Meteoritics and Planetary Science, traces the impact orbits of a number of observed meteorite falls, including several to previously unidentified source regions in the main asteroid belt. The study's lead author, Peter Jeniskens from NASA's Ames Research Center and the SETI Institute, describes the report as a decades-long detective story, with each meteorite impact providing a new clue. 10 years ago, Jeniskens teamed up with Hadrian de Villepoix and astronomers from Curtin University to develop the first outlines of a geologic map of the asteroid belt. By then, Curtin had already developed its now famous Outback Fireball network of cameras, and they assisted Jeniskens and colleagues in North America to build a similar network of all-sky cameras in California and Nevada. These are designed to capture and track the bright lights of meteors as they hit the Earth's atmosphere. Many other institutions, as well as citizen scientists, have participated in these efforts over the years and eventually created a global fireball observatory. Initially, de Villepot and colleagues tracked the path of 17 recovered meteorite falls. And many more fireballs were tracked using doorbell and dashcam video cameras by citizen scientists, as well as by other dedicated networks. Now altogether, the effort has now yielded some 75 laboratory-classified meteorites, each with an impact orbit tracked by video and photographic cameras. Jeniskin says that this is providing enough material to start to see some patterns in the direction from which meteors approach the Earth. Most meteorites originate from the main asteroid belt between Mars and Jupiter, where over 1 million asteroids larger than a kilometre orbit the Sun. Now, this massive collection of space rocks all originate from a much smaller number of larger asteroids, which have been broken apart in collisions, creating debris fields which litter much of the region. Even today, asteroids are colliding, creating new debris fields or clusters within these asteroid families. During their studies, the authors have found that 12 of the iron-rich ordinary H-type chondrite meteorites originated from a single debris field now called Coronis. It's located in the pristine main belt. Jeniskin says that these meteorites arrived at low-inclined orbits on orbital periods consistent with this debris field. Astronomers can measure how long ago these rocks were dug up from below an asteroid's surface by measuring the level of radioactive elements created by exposure to cosmic rays. And this cosmic ray exposure age in meteorites can be used to match the dynamical age of some of the asteroid debris fields. Scientists can determine the dynamical age of an asteroid debris field by measuring how far the asteroids of different sizes have spread over time. By measuring the cosmic ray exposure age of meteorites, they could determine that 3 of these 12 meteorites originated from the current cluster of the Coronis field. And the Coronis field has a dynamical age of 5.8 million years. And a further 2 came from the Coronis 2 cluster, which has a dynamical age of 10 to 15 million years. Another meteorite from this group may well be measuring the age of the Coronis 3 cluster, resulting in a figure of around 83 million years. Jeniskins and de Villepot also found a group of H-chondrites on steep orbits. They appear to originate from the Neil asteroid family in the central main asteroid belt, and it's been shown to have a dynamical age of around 6 million years. A third group of H-chondrites that have exposure ages of around 35 million years originated from the inner main belt. These are all thought to have originated from the Massalia asteroid family low in the inner main belt. Jenkinson says that the asteroid which created that cluster, 20 Massalia, is also an H-chondrite parent body type. Jenkinson and de Villepot find that the low iron L-type chondrites and very low iron LL chondrite meteorites also primarily come from the inner main belt. Scientists have long linked the LL chondrites to the Flora asteroid family on the inner side of the main asteroid belt, and this new work has now confirmed that is correct. Jenkinson proposes that the L chondrites originated from the Hertha asteroid family, located just above the Massalia group. But asteroid Hertha doesn't look anything like its debris. It's covered in dark rocks that were all shock-blackened, indicative of an unusually violent collision. The L chondrites experienced a very violent origin 468 million years ago, and since then these meteorites have showered the Earth in such numbers that they can be found throughout the geological record. Knowing from which debris field an asteroid belt meteorite originates from is important for planetary defence efforts against near-Earth asteroids. An approaching asteroid's orbit can provide clues about its origins in the main asteroid belt in the same way as a meteorite orbit does. But near-Earth asteroids don't arrive on the same orbits as meteorites. That's because they take longer for these to evolve into Earth-crossing orbits. But they nevertheless come from some of the same asteroid families. This is SpaceTime. And time now to check out the night skies of April on Skywatch. April is the 4th month of the year in the Gregorian calendar and the 5th in the early Julian calendar. The Romans gave this month the Latin name Aprilis. Although the name's origins aren't certain, traditional entomology suggests it's from the verb aperire, to open, as in it being the season when the trees and flowers begin to open as the northern hemisphere moves into spring. April is also Prevention of Cruelty to Animals Month, and so it's a good time to consider adopting a shelter pet or donating to an animal welfare charity. High in the southern sky during April, you'll find the Southern Cross and its 2 pointer stars Alpha and Beta Centauri. The more distant of the two pointer stars from the Southern Cross is Alpha Centauri, which also happens to be the nearest star system to our own. Located some 4.3 light-years away, Alpha Centauri actually consists of 3 stars. There's Alpha Centauri A and B, which orbit each other, and Proxima Centauri, which orbits the pair. And at 4.25 light-years distant is currently the nearest star to the Earth other than the Sun. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Like the Sun, Alpha Centauri A is a spectral type G yellow dwarf star. It's slightly bigger, having about 1/10 more mass than the Sun, and has about 50% more luminosity. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars of all are spectral type M red dwarf stars. Each spectral classification is further subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and then a Roman numeral to represent luminosity. So, our Sun is a spectral type G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars called brown dwarfs. These are sometimes born as spectral type M red dwarf stars, but become brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are around 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. Orbiting in a binary system with Alpha Centauri A is Alpha Centauri B, a spectral type K orange dwarf star, a little smaller and cooler than the Sun, with about 0.9 times the Sun's mass and about half its luminosity. Alpha Centauri A and B orbit each other around a common centre of gravity every 79.91 Earth years. The distance between the two stars varies between roughly that of Pluto and the Sun and that of Saturn and the Sun. The third star in the system, Proxima Centauri, sometimes called Alpha Centauri C, is a spectral type M red dwarf star, with roughly 1/7 the diameter and about 1/8 the mass of the Sun. It takes around 550,000 Earth years to orbit Alpha Centauri A and B. The nearer of the two pointer stars to the Southern Cross is Beta Centauri, also a triple star system, but this one located a far more distant 390 light-years away. All 3 are massive young blue stars, far larger and more luminous than the Sun. 2 of the stars, named Beta Centauri AA and Beta Centauri AB, orbit each other, while the third star, Beta Centauri B, orbits the primary pair every 1500 Earth years. Beta Centauri AA and AB are known as a spectroscopic binary, orbiting each other every 357 Earth days. Spectroscopic binaries are double-star systems orbiting each other so closely and at such an angle that they can only be visually separated, from our point of view here on Earth at least, by their spectroscopic signatures. Both these stars are now reaching the end of their time on the main sequence and will soon run out of the core hydrogen they use for fusion, the process which makes stars like the Sun shine. The two pointer stars, Alpha and Beta Centauri, are named after Chiron, the centaur, a mythological Greek being half man, half horse. Chiron taught many of the Greek gods and heroes, but was placed among the stars after accidentally being shot with a poison arrow by Hercules. Next to the pointer stars is the spectacular Southern Cross, or Crux, the smallest but one of the best known of the 88 constellations in the sky. The Southern Cross is considered an important constellation for navigation and is featured on the flags of several nations, including Australia, Brazil, New Zealand, Papua New Guinea and Samoa. In April, the Southern Cross lies on its side in the early evening, but becomes more and more upright as the night progresses. The bottom and brightest star in the Southern Cross is Alpha Crucis or A Crux, which is actually a multiple star system located 321 light-years away. It consists of 3 stars, A1 Crucis, which is a spectroscopic binary, and A2 Crucis. A2 Crucis and the primary star in A1 Crucis are both spectral type B blue stars, with surface temperatures of 26,000 and 28,000 Kelvin respectively. The two components orbit each other every 1,500 Earth years at an average distance of around 430 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometres or 8.3 light minutes. The spectroscopic binary A1 Crucis is thought to comprise 2 stars, with about 10 and 14 times the mass of the Sun respectively. The pair orbit each other every 76 Earth days at a distance of around 150 million kilometres, in other words, 1 astronomical unit. The masses of A2 Crucis and the larger component of A1 Crucis are expected to eventually explode as core collapse supernovae, ending up as neutron stars, while the smaller component of A1 Crucis could survive as a white dwarf. The left-hand and second brightest star in the Southern Cross is called Beta Crucis, and it's also a spectroscopic binary, consisting of 2 stars orbiting each other every 5 Earth years at an average distance which varies between 5.4 and 12 astronomical units. Beta Crucis is located some 280 light-years away. The primary star, Beta Crucis A, is a spectral type B Beta Cephei variable blue star, which changes in brightness over a period of around 4 to 4.5 hours. It has about 16 times the Sun's mass, about 8 times its diameter, and a surface temperature of some 27,000 Kelvin. By comparison, our Sun has a surface temperature of just 6,000. The second star in the system, Beta Crucis B, has about 10 solar masses. A third companion has also been detected in the system. However, it appears to be a low-mass pre-main sequence star which hasn't yet commenced nuclear fusion. Near Beta Crucis is the spectacular young open star cluster known as the Kappa Crucis cluster, or NGC 4755, and more commonly referred to as the Jewel Box, the name given to it by famous 18th century astronomer John Herschel. Open star clusters are groups of stars which were originally all born at the same time out of the same collapsing molecular gas and dust cloud. Although somewhat still gravitationally bound to each other, stars in open clusters eventually separate, moving to other parts of the galaxy. As the name suggests, the Jewel Box is a stunning collection of more than 100 bright, colourful stars, located some 6,440 light-years away, although its exact distance is somewhat difficult to determine because of the nearby Coalsack Nebula, which obscures some of the light. The Coalsack is a dark nebula containing lots of gas and dust blocking out background stars. In Australian Aboriginal Dreamtime legend, the Coalsack forms the head of the Emu constellation, with the dark dust lanes of the Milky Way forming the emu's body and legs. The central parts of the Jewel Box are framed by bright stars making up an A-shaped asterism. These are among the brightest known blue, white and red supergiants in the Milky Way. Gamma Crucis, which is located at the top of the Southern Cross, is the third brightest star in the constellation. It's also one of the nearest red giants to our solar system, located just 88.6 light-years away. Although only 30% more massive than the Sun, its expanded outer envelope is bloated out to some 84 times the Sun's radius, and is radiating some 1,500 times more luminosity than the Sun. As a red giant, no longer on the main sequence, Gamma Crucis is nearing the end of its life. Its surface temperature is some 3,626 Kelvin, and it has a prominent reddish-orange appearance. The star on the right-hand side of the Southern Cross is Delta Crucis, a massive, hot and rapidly rotating star that's in the process of evolving into a red giant and will eventually end up as a white dwarf, the stellar corpse of Sun-like stars. Delta Crucis is located some 345 light-years away and has about 9 times the Sun's mass and 8 times its radius. It's presently radiating at around 10,000 times the luminosity of the Sun at an effective temperature of 22,570 Kelvin, causing it to glow with a blue-white hue. The smallest star in the Southern Cross is Epsilon Crucis, which is located in the space between Delta and Alpha Crucis. It's a red giant, some 228 light-years away. It has about 1.42 times the mass of the Sun and about 32 times its radius. Its surface temperature of 4,148 Kelvin means it's sometimes referred to as an orange giant. The Southern Cross is at its highest point in the southern sky this time of year and is pointing directly at the southern celestial pole. It's within the constellation Centaurus the Centaur, the half-man, half-horse of Greek mythology we mentioned earlier. The creature is holding a bow loaded with an arrow. The Centaur's front leg is marked by the two pointer stars Alpha and Beta Centaurus. His back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster visible with the unaided eye from dark locations. Unlike open star clusters, globular clusters are tightly packed spheres containing thousands to millions of stars, which were originally all thought to have been born at the same time from the same molecular gas and dust cloud. Omega Centauri is about 16,000 light-years away. It's one of the largest and brightest of the hundreds of globular clusters known to orbit around the Milky Way galaxy. Centaurus was included among the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. The constellation Orion the Hunter is still clearly visible in the northwestern sky this time of year, with its rectangle of 4 stars surrounded by a central trio of stars which form Orion's belt. To the right or east of Orion is the constellation Gemini and its 2 brightest stars, Pollux and Castor. This time of year, the Gemini twins are almost directly due north for southern hemisphere sky watchers. The higher of the 2 stars, Pollux, is a red giant, some 11 times the diameter of the Sun and located just 34 light-years away. The other star, Castor, is much further away, some 51 light-years. Look to the east and you'll see the star Regulus, the brightest star in the constellation of Leo the Lion. Regulus, which means Little King, is located 77 light-years away, and it's about 3.5 times as massive as the Sun and about 140 times as luminous. Regulus is a binary companion star, which takes 130,000 years to orbit the primary. To the right of Regulus, and virtually due east in the sky right now, is the star Spica. Located directly below the 4 stars in the constellation Corvus the Crow, Spica is the brightest star in the constellation Virgo. Also known as Alpha Virginis, it's the 16th brightest star in the night sky, and is another spectroscopic binary, comprising 2 stars closely orbiting each other every 4 Earth days. In fact, the 2 stars in Spica are orbiting so close together that the gravitational interaction between them has caused them to become rotating ellipsoidal variables, distorting them into the shape of a rugby league or gridiron football. Light from this binary changes in brightness as the 2 stars orbit each other, exposing their elongated hemispheres to us. Spica is located some 260 light-years away and is some 2,000 times as luminous as the Sun. Spica means ear of wheat, which Virgo is holding in her hand. It's so named because it marks the start of the harvest season in the Northern Hemisphere. The primary is a blue giant variable Beta Cepheid, which undergoes small rapid variations in brightness because of pulsations in the star's surface thought to be caused by the unusual properties of iron at temperatures of 200,000 degrees in the stellar interior. It has about 10 times the Sun's mass and about 7.5 times its diameter. Once a spectral type B blue-white main sequence star, it's now pulsating rapidly, rotating at more than 199 kilometers per second over a 0.1738 Earth-day period. It's one of the nearest stars to the Earth, which is expected to end its life as a Type II core collapse supernova. The second star in the system is also thought to be a spectral Type B blue-white giant, about 7 solar masses and 3.6 times the Sun's diameter. Okay, going back to the Southern Cross and looking to the right or west, you'll see the star Canopus. It's the second brightest star in the night sky after Sirius. Even though Canopus is 312 light-years away, it looks incredibly bright because it's huge, 100 times the diameter of the Sun and 10,000 times as luminous. This year's second major meteor shower, the Lyrids, will peak on April the 22nd and 23rd. The Lyrids appear to radiate out from the constellation Lyra, close to the star Vega, one of the brightest stars in the sky this time of year. The source of the meteor shower are particles of dust and debris shed by the long-period comet C1861 G1 Thatcher. Sky watchers in the Northern Hemisphere get the best view of the Lyrids. However, listeners at mid-Southern Hemisphere latitudes can also see the shower between midnight and dawn. Patient observers will be rewarded with around 18 meteors per hour before dawn from dark sky locations. And now with a look at what else is happening in the April night skies, we're joined by science writer Jonathan Nally.
G'day, Stuart. Well, we're now into autumn here where I live, which will be spring in the northern half of the planet, of course. And for me, the sun is setting earlier and the nights are becoming longer, which means it's perfect conditions for stargazing. So we'll start with the good old Southern Cross, which we can find in the southeast, about a third to halfway up from the horizon, sort of after sunset, an hour or two after sunset. It's lying on its left-hand side at the moment, so it looks like a kite that's on its left-hand side. But as the night goes on and the Earth turns a bit more on its axis, you'll see that it becomes more upright. We'll just talk about the cross for a sec. The Southern Cross appears to have four main stars, and they make up the shape of this kite. Two of those stars are solo stars, but the third of them is made up of either two or three stars. It's either a binary star system or a trinary star system. They're so close together that to the unaided eye, they just look like one star, of course. But the fourth star, and it's the brightest of the four stars, is actually a six-star system. There are six stars all sort of circling each other in this star, which is called Acrux. It's really amazing that how many stars out there are part of binary or trinary or quaternary systems. It's the norm, really, to be in a binary star system or triple star system or something. So our sun is a bit of an oddity being on its own. But you don't see this. You don't think about this when you look up and look at some of the stars in the night sky. You don't think, oh, that one's part of a six-star system or that one's part of a four-star system. But a lot of them are. Now, right next to the Southern Cross, there's a dark patch that's known as the coal sack. This was once thought to be a gap or a hole in the Milky Way a long time ago, but really it's just a huge region of gas and dust that's very thick, and it blocks our view of the stars behind it, so we can't see the background stars. Now, in order to see the coal sack, you do need to have some clear, dark skies. City skies probably don't cut it because all the light pollution just drowns stuff out anyway. So the thing is that the Southern Cross, for instance, that there is a fifth star in the Southern Cross, but a lot of people in cities can't see it. This light pollution is now so bad that, in fact, I think from where I am, I can't even see the fifth star.
It's very sad, isn't it?
It is really sad. And, it's one of the funny things is that here in Australia, there's a piece from one of the government departments, they have a software service that's used for navigation systems and surveying systems, and it's named after this fifth star. And the irony, of course, is that it's used to be used for finding your position and navigating, but most people now can't see it because they live in cities that are so light polluted that this star is invisible. That's the way it goes, I'm afraid. And speaking of brightnesses and not being able to see things, you might think that stars, when you look up, you see stars and they all look much the same brightness. And you'd think that because they're of similar brightness, they'll all be roughly the same distance from the Earth. But that's not the case. We've got some stars that are intrinsically very bright, but they might be very far away, and that therefore they seem dim. But then you have other stars that are dim, but they're very close, so they seem brighter than the bright ones are. So the four stars of Southern Cross, for instance, they range in distance from us from about 90 light years to about 340 light years. So you can't really tell the distance of a star from the Earth just based on its brightness. You've got to dig a bit deeper than that. So brightness does not equate with distance. Now, speaking of a bright star, up really high in the south at the moment, there's a bright star called Canopus. This is the brightest light in the constellation of Carina, and it's actually the second brightest star in the night sky. And it's no wonder, talking about brightness, because even though it's more than 300 light years away, intrinsically it's more than 10,000 times brighter than our sun, and it's 70 times as big. Now, that's really big. Imagine that 10,000 times brighter. That's why it's the second brightest star in the night sky, even though it's 300 light years away. The night sky's brightest star, Sirius, is also very easily visible at the moment. It's practically overhead in the early evening if you live at the latitude of Sydney in the southern hemisphere. Comparing Sirius to Canopus, Canopus being that really big one, Sirius is only 25 times brighter than the sun, but it's only 8.5 light years away compared to 300. So that's why it seems a bit brighter to our eyes. Now, not far from Sirius, you've got the constellation Orion with its two bright stars, Rigel and Betelgeuse, and there are three stars in a row known as Orion's belt. Now, if you thought Canopus is impressive, being 10,000 times brighter than the sun, well, Rigel beats that easily. Scientists are not quite sure of the number for some technical reasons. There's a bit of a range of estimates of how bright it intrinsically is, and that ranges from 60,000 times brighter than our sun to 360,000 times brighter than our sun. I mean, that's just berserk. And the other star I mentioned, Betelgeuse, it's no slouch either. It's about 60,000 times brighter than the sun. But with Betelgeuse, it's the size that really impresses. It's somewhere between about 640 and 760 times as big as our star, which is just crazy. It's hard to imagine, isn't it?
If you put it in the centre of our solar system, its outer limb would be roughly where Jupiter is.
Yeah, basically. Yeah, it'd gobble up Mercury, Venus, Earth, Mars, the asteroid belt, pretty much all the way out to Jupiter. That's how big it would be. It's just unimaginable. There are some big, big stars out there. Now, let's look at the planets. If we take a look to the north, at least from here in the southern hemisphere, about a third of the way up from the horizon, you'll find what appears to be 3 stars in a row. The 2 whitish ones are actually stars. They're the stars Castor and Pollux. But the orangey-looking one is the planet Mars. Okay? You hear this thing quite often that when you look up at the night sky, stars twinkle and planets don't. And the explanation usually given for that is that stars are so far away that they are effectively point sources, like a tiny pinpoint of light. And that when the light comes through the Earth's atmosphere, it gets interfered with by air currents and things. So that's what makes stars twinkle. Whereas planets, even though you can't make out their size with the unaided eye, they do have a bit of a size, and therefore that doesn't get interfered with quite so much. So that's the explanation usually given. But when stars and even planets are low down towards the horizon, even a planet will twinkle. I remember getting a phone call one night from a mate of mine, and he said every night out there, he lives near the water, every night out over the water there's this red star, but it changes colour and it goes red and green and white, and it's there every night. And is it the Air Force doing something? What could it be? And I looked it up, and it was just Mars. But because it was down low on the horizon, the light coming through our Earth's atmosphere, the Earth's atmospheric currents were distorting the light basically and making it flicker. So even planets can twinkle, if you like.
Is that why the moon looks bigger on the horizon than it does when it's high up in the sky?
This is the moon illusion, and I don't know anyone's ever really got to the bottom of this. There are all sorts of ideas about why the moon appears to be bigger, because it's, you can compare it against houses or trees or the horizon or whatever, so it seems to have a discernible, not a discernible size, but, something you can compare it against. Whereas when it's up there high in the night sky, it's just an empty sky, so you can't really get a good comparison against anything else. I mean, the moon's only half a degree across. I mean, from horizon to horizon, if you drew a line from the horizon up overhead down to the other horizon, that of course that is 180 degrees. So you could stack 360 moons all the way from one horizon to the other. It's actually really small. As for the moon illusion, the so-called moon illusion, why the moon appears bigger on the horizon, I really don't know the answer. There are all sorts of things with those, but
might have more to do with our brains and the way our brains perceive things than the moon.
I suspect there's a lot of that. Yeah. I mean, you can do a test. If the moon's down near the horizon, have a look and see how big it is, and then get a cardboard tube and look at the moon through the cardboard tube so you can't see anything else around it, no houses and trees and things, and see whether it seems quite as big.
I've actually measured it on the horizon compared to when it's high in the sky, and it's exactly the same size, but it just doesn't look it. It's weird.
That's right. Yeah, there's something in our brains that does it. So anyway, that's the moon. Now over to the northwest, again looking from the southern hemisphere, so to be southwest if you're in the northern hemisphere, there appears to be a bright white star, but it is in fact the planet Jupiter. Now, if you have even just a pair of binoculars, take a look at Jupiter. You won't be able to make out anything on the planet itself. It'll just look like a bright star. But you should be able to see up to 4 tiny pinpricks of light, either to its left or right or both. It might be 3 on one side and 1 on the other, or 2 on one side and 2 on the other, or whatever. Now, these are the 4 moons discovered by Galileo. And by looking through a pair of binoculars, you've got about the same optical power as Galileo had with his first little telescope. In fact, your binoculars would be far better quality than Galileo's telescope was, but you'd have about the same magnifying power. So, have a look at Jupiter, even through a pair of binoculars, and you'll see these tiny pinpricks of light. They're very noticeable. They're very, very noticeable. If you go out and do it every night after night for a while, you'll see that these little pinpricks of light will have moved because they're orbiting around Jupiter. And a lot of astronomers like to do this, of course, with their telescopes. And what you can see is, for instance, sometimes when one of these moons goes around behind Jupiter and goes into its shadow, it just winks out. It just disappears because it's gone into the shadow behind Jupiter and just vanishes. And then it'll reappear sometime later on the other side when it comes back into the sunlight again. So that's fun to watch, but it does take a little while, so you need to allow some time. Now, to see the other bright planets, the other 3 bright planets, you'll need to be up before dawn. this month and looking to the east. Saturn is the first of them to rise at about 5:30 a.m. daylight saving time, at least here in Australia, followed around about 20 minutes later by both Mercury and Venus. Now, Saturn's fairly bright and it has a slightly yellowish tinge, so it should be pretty easy to identify. Mercury is quite small and dim. Venus, on the other hand, is big and bright. Now, if you're up early enough to spot these, you'll see that they're going to be in the beginning of the dawn glow as the sunrise approaches and the sky is starting to lighten. And as it gets lighter and lighter, Mercury and Saturn will quickly fade into that dawn glow. But Venus will linger a bit longer because it is really quite bright. And then the sun will come up, of course, and it will drown it out. Although, yeah, you can actually see Venus during the daytime. I've seen Venus during the daytime. When it's up high in the sky in a crystal clear, bright blue sky, Venus is actually bright enough to be seen with the unaided eye, but you've got to know exactly where to look. So if you've got a way to pinpoint exactly where it is, you look up and you think, oh, goodness, yes, there is a tiny thing that looks like a star up there. When you look directly at it, you know it's there, you can see it, and you think, wow, that is Venus. But because it's usually close-ish to the sun, people, of course, don't bother looking up. Don't go looking up with a pair of binoculars or a telescope during daytime if the sun's anywhere near. Please don't do that because just one wrong move and you might blind yourself. So on that happy note, Stuart, that's the sky for April.
That's science writer Jonathan Nally, and this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.